Hi everyone, and welcome to the second part of our CS2100 lecture on functions and relations. So in part one, we covered the basic definitions of functions and relations, and formalized a few properties, while in this part two, we will expand that with definitions of function and relation inverses, and so on. So let's get started. So let's first specify inverses of relations. So given a relation R that is a subset of A Cartesian product with B, R minus 1 is called the inverse of R and is defined as a subset of B Cartesian product with A, such that the pair XY element of R, if and only if the pair y of x is an element of R minus 1. So here is an example. So what is the inverse of this relation that is given in this arrow diagram? Well, it's really simple to define it. You do it by just reversing the arrows in the diagram. So you know, the first arrow would point in a direction and so on. What are the inverses of functions? It's very similar to inverses of relations. So functions f that maps A to B and g that maps B to A are inverses of each other when f of A is equal to B, if and only if g of B is equal to A for all A element of E and B element of B. For all A element of A and B element of B. So we said that G is the inverse of F and F is the inverse of G. So F performs an action and G undoes the action. The inverse of F is also written as F minus 1. Note here that both F and G must be functions. So we have an example here of function f that is drawn using an arrow diagram. And now the question is there a way to define a function g that is equal to f minus 1? And how would we achieve that? The same as for relations. We could try to simply flip these arrows in the other direction. However, notice that we have a problem here, because now that when B becomes a domain, we have this one element of the domain that is not being mapped to anything, and therefore that would not be a function anymore. So this example illustrates that not every function has an inverse, and we'll talk about this more later in these lectures. So how do we do a proof that two functions are inverses of each other? So let's say we have the following proposition. Let f map z to z and is defined as f of x is equal to x plus 3, and g also maps z to z with g of y is equal to y minus 3. Then we want to show that for all a b element of z, f of a is equal to b if and only if g of b is equal to a. So remember from our lectures on proofs what if and only if means. So if and only if indicates implications in both directions. So we have to show one direction and the other direction. And that is happening in these claims 1 and 2. So in claim 1, we are proving that if f of a is equal to b, then g of b is equal to a. So how do we do this? So let a and b be given such that f of a is equal to b. Then by substitution, and from the rule of f, we know that b is equal to a plus 3. And then if we rearrange this a little bit, we get that a is equal to b minus 3, which is exactly the rule of g. And therefore, a is equal to g of b. So that proves one direction of the implication. And now we have to still prove the other one. So if g of b is equal to a, then f of a is equal to b. So now we are given a and b such that g of b is equal to a. And by substitution into the rule of g, we get that a is equal to b minus 3. When we rearrange that, we get that b is equal to a plus 3, and therefore f of a is equal to b. And this concludes our proof that these two functions are inverses of each other. Okay? So let's do a practice problem and prove another inverse. So in this case, we have this function f that maps reals into reals with the following rule. F of x is equal to 3x plus 5 for all x in R. And then here we first want to find the rule for the inverse function g, and then we have to prove that our answer is correct. So let's first find what g would be. So we have f of x is equal to 3x plus 5. So let's say that y is equal to 3x plus 5. From that, we get that y minus 5 is equal to 3x, or x is equal to y minus 5 divided by 3. So that is our rule for g. So g is a function which also maps R into R. And the rule is that g of y is equal to y minus 5 divided by 3. Now, to prove that these functions are indeed inverses of each other, we have to prove both directions, as in the previous slide. So direction 1 is that if y is equal to f of x, then g of y is equal to x. And direction number 2 is the opposite of this. If x is equal to g of y, then y is equal to f of x. So let's do the first one. So we have x and y element of R such that y is equal to f of x. So that is given to us. Now if we plug in the rule, we get that y is equal to 3x plus 5. From here, we get that 3x is equal to y minus 5, or x is equal to y minus 5 divided by 3. And from here, it follows, because that's the same as the rule for g, that x is equal to g of y. So that shows one direction. Now the other one, we have x, y, element of R, such that x is equal to g of y. From that, when we plug in the rule, we get that x is equal to y minus 5 divided by 3. If we multiply this by 3, we get that 3x is equal to y minus 5. And from here, we get that y is equal to 3x plus 5. If we look up the rule for f, we can see that this matches it. And so we show that y is equal to f of x, and that concludes the second claim. And this finishes our proof. Okay, let's now talk about composition of functions. So for functions f that maps a to b and g that maps b to c, the function h that maps a to c, where h of x is equal to g of f of x, is the composition of g with f. We often denote it using this little circle. So h is equal to g circle f, or h of x is equal to g circle f of x. And we state it as g of f of x. So here are some examples. If f maps integers to integers, and the rule is f of m is equal to 5m minus 7, and g also maps integers to integers, and the rule is g of z is equal to z plus 1, then what is f so what is then f of g of 1? How do we calculate this? Well, first we imply g to 1. So g of 1 is equal to 2 times 1 plus 1, which is equal to 3. And then we apply f to that. So we have to compute then f of 3, that is equal to 5 times 3 minus 7, which is equal to 8. And so this is the answer. Be careful here that order matters. And you start with the function that is the most on the most right. Let's say it like that. So another question we can ask is how can we express f circle g of x? It's pretty simple to compute this as well. So we know that g is 2 times z plus 1, and we plug this into f. So we have 5 times that minus 7, and that is then equal to 10z plus 5 minus 7, and that's equal to 10z minus 2. So f circle g of x is equal to then 10x minus 2. Okay, so that's composition of functions. We can use again an arrow diagram to represent this. So if we have these two functions f and g that this arrow diagram defines, then f circle g simply connects domain of the first function, function f, with the codomain of the second function by following the arrows through this set B that connects them. So if you look what one maps into, well, f maps 1 into B, and then G maps this B into Q, and so G circle F maps 1 into Q, and so on. So this illustrates composition using arrow diagrams. Okay, another concept is identity function. So an identity function on the set A is denoted using I of A, and it maps set A to itself. And the property of the identity function is that EA of x is equal to x for all x element of A. So it maps every element of A into itself. If we represent this relation, it will be defined using the set x comma x, where x is an element of A. And often we simply write I of x, we drop the A subscript. So what is the inverse of function I of A? Well, it's pretty easy to see that the inverse of I of A is I of A itself. So the inverse of an identity function is the function itself. So here is an example of an identity function. Let f map rationals into rationals, and the rule is that f of x is equal to 2 over 5 times x minus 2. And g has the rule g of y is equal to 5 over 2 times y plus 5. And now if we compute the composition of g and f, we get, after we work it out, that the rule for the composition is just x. So g, circle L, is equal to the identity function. Is then f circle g equal to the identity function as well? Well, we can quickly compute this. So we have f circle g of x is equal to f of 5 over 2 x plus 5, and that is equal to 2 over 5 times 5 over 2 x plus 5 minus 2. Okay, that's equal to x plus 2 minus 2 is equal to x. So the composition of f and g is also equal to the identity function. Okay, recall that functions f and g are inverses of each other when f of a is equal to b, if and only if g of b is equal to a. So how can we restate this using composition and identity? Let's see. We can say that functions f and g are inverses of each other if and only if g composed with f is equal to identity function and f composed with g is equal to identity function. So we can actually prove this, and here I sketch out the proof. So there will be two cases because we have if and only if, so we have to prove both directions. And you can study this proof at home. I'm not going to walk through all the steps now. But it's a pretty easy proof. It just has a lot of cases. And here is the continuation of the proof for case 2, which is the other direction. And so this theorem is called the inverses theorem. Okay, so we saw how we can compose functions. In a similar way, we can compose relations as well. So let R1 be a relation with domain A and codomain B, and R2 be a relation with domain B and codomain C. Then the relation R3, which is defined as the set of pairs AC, such that if there exists B element of B, where A pair AB is an element of R1 and BC is an element of R2. Then this R3 is the composition of R2 with R1. And we write it the same way as we write for functions using this little circle. And we say R2 of R1. So this is composition of relations.